When we are introduced to the determinant of an n by n matrix in linear algebra, one way we can define the determinant involves permutations of the first n positive integers 1, 2, 3 through n. What is meant by permutation is an ordered arrangement. For example, the permutations of the numbers 1, 2, and 3 are 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. There are only 6 distinct or different permutations of those 3 numbers, and it's easy to see why that is true. We have 3 choices for which number goes first. Once that is chosen, then there are only 2 to pick from for the second spot. And once the first 2 spots are chosen, there's only 1 choice left for which number goes third. When we multiply these choices, we get 3 times 2 times 1, which is 6. We can use the factorial notation to write this calculation as 3 factorial equals 6. And in general, the number of distinct permutations of the first n positive integers is n factorial. Along with understanding what a permutation is and how many exist for a set of numbers, when we define a determinant, it is also important to know whether a given permutation is even or odd. A permutation is even if the minimum number of interchanges of 2 consecutive elements necessary to return the permutation to its natural increasing order is an even number. A similar statement can be said for an odd permutation. For example, to return the permutation 3, 2, 1 to its natural order 1, 2, 3, we need 3 interchanges. 3, 2, 1 to 2, 3, 1, where I've interchanged the 3 and 2, and then again to 2, 1, 3, where I've interchanged the 3 and 1, and then finally 1, 2, 3, where I've interchanged the 1 and the 2. Thus, 3, 2, 1 is an odd permutation, along with 1, 3, 2 and 2, 1, 3. The even permutations are 1, 2, 3, 2, 3, 1, and 3, 1, 2. When we define the determinant of an n by n matrix, we associate a positive sign with even permutations and a negative sign with odd permutations. Now let's observe where the permutations are in the definition of the determinant of a 3 by 3 matrix. If we define a matrix A as seen here, then the determinant of A is defined as this sum. There are 6 products involved in this sum, with 3 being positive and 3 being negative. In each product, there are 3 terms. Notice that the first numbers in each subscript keep the pattern 1, 2, 3. I've rewritten that sum, and I've highlighted each of the first subscripts in red, and you can notice that they are all 1, 2, 3 with each of the 6 products. And when we consider the second numbers in each subscript, we get the 6 different permutations of 1, 2, 3. Notice that the negative terms in the determinant come from the odd permutations we described before. We can further generalize the determinant of an n by n matrix using all we have discussed, but we will leave that for your linear algebra class. What we will consider for the rest of this video is where these permutations have appeared in music, specifically with the ringing of church bells in England. In the English tradition of bell ringing, called change ringing, there are different bells tuned to different notes, and only one bell is rung at a time. It is a centuries-old tradition, with bells rung by hands pulling on ropes tied to wheels. And because of the large size of the bells, each can only ring about once every 2 seconds. If there were 3 bells, with the highest pitch notated as 1 and lowest pitch notated as 3, we could ring the 3 bells in descending pitch order as 1, 2, 3, and repeat. Listening to the same order of notes over and over loses its interest pretty quickly, and so changes to the ringing order can be introduced. But again, due to the size of the bells, these changes can only occur with adjacent bells. For example, we could start with 1, 2, 3. The conductor could call out a change for bells 1 and 2 to switch their order, and then we would hear 2, 1, 3. The conductor could again call out a change for bells 1 and 2 to switch, and we would be back to the natural order. However, there is a way to run through the extent of all 6 permutations by changing only 2 adjacent bells each time. The only other way to ring the extent of all 6 permutations is to follow these changes backwards. Since each bell can be rung every 2 seconds, it only takes 12 seconds to hear the extent of all 6 permutations. But as the number of bells increases, the number of permutations really grows due to the nature of the factorial. For a church with 7 bells, there are 7 factorial or 5040 permutations, which would require 2 hours and 48 minutes to hear the full extent. Most performances of bell ringing before a church service are a quarter of this. We could even make a shorter performance using 3 bells. We could hear a 4-second performance by just hearing our first example of 1, 2, 3, 2, 1, 3, and then back to 1, 2, 3. If we have 4 bells, we can hear a short performance through these changes. The longer and shorter performances were early examples of what we learn about groups in algebra, and some of the things we learn in linear algebra, like vector spaces and transformations, also have ties to what is later learned in group theory.